You are given an array and you have to split it into the maximum number of parts such that each part has equal median and each part has odd length. For example, in this array, suppose you split it into the first block here, second block, third block here, and fourth block, and the median of all the elements in this block should be equal to x. Median of all the elements in this green block should also be equal to x. All the elements in the yellow block should have a median x, and all the elements in the white block should have a median x. So your goal is to maximize the number of blocks that you can create such that each block has an identical median, which could be anything. So take a minute to pause this video to think about how you would approach this problem on your own before jumping into the solution. And note that each block that you create has to be of odd length, because in odd length there is no ambiguity for a median. So if this is the median, then half the element will be smaller than the median and half the element will be bigger than the median, and the median would be the central element of the array. Because for even length there is some confusion regarding which element should be considered as the median, whether it is this one or this one or the average of this one. So we are simplifying things in this problem and we are saying that, okay, assume that there is no concept of median for even length array. So just assume that you only have to deal with odd length array, as well as all the blocks that you are creating, they should also be of odd length so that there is no ambiguity for which the median element is. So let's start out by how you would approach this problem first. So along the way, we'll learn some facts about median that can help you solve future problems related to median. So we'll learn about some techniques that works, but also some techniques that looks like it should work, but in reality, things might be different. So let's talk about some observation for median. So first observation is median of any block will be an original element of the array. Will be an element of the original array. So why is this true? Because of the fact that if you have n integers in a set and odd integers in a set, suppose this is one integer, second, third, fourth, fifth, sixth, seventh, etc., then the median resides inside this set. And why is that statement true? It's simply because how do you find the median? You sort all the elements and you locate the element which is at the central position. So half the element are smaller and half the element are bigger. So the median has to be in the set. So even though we do not know what should the optimal choice of x be for each of these blocks, we can kind of assume that x has to be in the array. So we know that x will definitely belong to the array. So instead of guessing the x that can provide us the maximum number of blocks, can we not just try all the x? Try all x. So this is the first property of the median that you will utilize. That is, if you have these many elements in the array, so you ask a simplified version of this problem. You fix this element a of 0 as x, and you ask the question, is it possible to have several blocks whose median is equal to x? And then you iterate x from a0 to a of n. But how does this simplification actually help us solve problems? So first thing is that you will be able to try out all the possibilities of x that you right now do not know. And the second and the most powerful observation is that it transforms the problem from median to something else that we are already familiar with. So in the next slide, we will see how it can do the transformation into a world that we are very familiar with. But for now, assume that you are going to try this algorithm. You have all the elements in the array lined up. Like let's say this is the A0, this is A of 1, this is A of 2, and so on. So first you will fix A1 as X, and then you can try out all the possibilities of creating the maximum number of blocks when the median of each block is equal to X. And what will be the time complexity of this algorithm? So suppose for a fixed X, you can find out the answer in f of n. Then the time complexity would become n into f of n. So notice that right now we haven't even discussed the algorithm of how we will find out the answer when this X is fixed. But if you know that it can be solved in f of n, then the overall time complexity would become n into f of n. So if you have a linear algorithm to compute for a fixed X, then the overall time complexity becomes O of n square. So can we fix X smartly? Like, can we fix X as the highest element or the smallest element, or can we even do a binary search over X to get this answer? So let's first discuss that whether it is actually necessary to try out all the possibilities of X, or can we do a binary search or some similar optimization to maybe just try a couple of possibilities for X. So now we talk about another fact of median. So this is observation 2. So the observation 1 was that median has to belong to the array. And for observation 2, suppose you have fixed this X. Then you will create several blocks. This is the first block, and the median for this block is X. This is the second block. Median for this is X. Block size will be different, of course, but then median will remain same, because that is what the problem demands. This is the third block with median X, and this is, like, let's say the fourth block with median X. Now let's see what happens when you merge a block. If you merge a block, then if you notice the interpretation of median, what did I say before? That median represents the central elements. So if you have X over here, this means that half the element are smaller than X and the remaining half is greater than X. And this is true for this blue block. Now when you add this yellow block into this set, like when you merge them, so now right now we are trying to merge. Right now we are trying to merge these two blocks. Then even in this block, this same property will follow, like half these elements are smaller and half these elements are bigger, and then you have X. So you can see that for each element of this block that you are adding, you will have for each smaller element there is a corresponding higher element for comparison with X. So if you start adding all the yellow elements here, then you will see that one element goes here, but its counterpart, which is the higher element, goes here, because if X is the median, then every element will have a pair that cancels out. So when you merge the blocks, half the elements will land on the lower half and half the elements will land on the upper half. So the median of this merge still remains X. So you can see that merging a block does not change median. Does not change median. And again, why is this true? Because there are half elements smaller than X, half elements bigger than X. Same property here. So if you combine this smaller than X, they will also have, like if you combine these two, they will also be equal in number to the elements that are bigger. This means that if you repeatedly keep on merging all the blocks, you will get the entire array. So you can merge all the blocks to get the original array. And by inductive reasoning, you can see that if the median of the first to merge is equal to x and you have created a bigger block, then the median of the next merge will also be equal to x. So if you keep on doing this process, you will get the entire array. And the original array had a fixed median, which you can determine by sorting the original array and figuring out this x. This means that what we were trying to do earlier, this part, that trying out all the x, that was actually an overkill, because if an optimal partition exists where each block has equal median, then each block should have x equal to the original median. This is also true. So now you can see that we don't actually have to increase the time complexity from f of n to n. The overall time complexity would still be f of n only, not n into f of n, because we actually don't have to try out all the different possibilities for x. So just let me formalize this second observation. So second observation was basically saying, if you insert a low comma high pair into a set, the median does not change. And what do I mean by low and high? Because low and high are relative, right? But low and high with respect to what? So with respect to, so I am talking about this scenario where you have a set and this element is your median, you have labeled it x, and half the elements are bigger, half the elements are smaller. So we say that if you insert a low comma high pair, low comma high pair means the first element is less than x and the second element is greater than x. So if you do this insertion, then the median of the set does not change. And if you repeatedly follow this process, then each block can be merged back and you retrieve the original array. So this means that the whatever the median of the original array is, each block will have the same median. So now we only have to find out, can you create several blocks and what is the maximum number of blocks that you can create with median equal to m, which is the median of the original array. But like I said earlier, that every time you want to solve median related problem, you should always try to come to a familiar word, right? Transformations, you should always try to do some transformations to a familiar world, because median problems are usually hard to solve, but once you have done some transformation and converted to a different version of that problem, you will be able to solve it using some known techniques. Because there is no, actually, if you think about it, there is no playbook for solving median related problems, but the transformation that we are going to see next, that will help you see why this transformation can actually help you with solving the problem. So what is the transformation that we could do? So you can see that we have defined median as this construct, like you have some central element sitting over here and half the elements are smaller and half the elements are bigger. But if you say that half the elements are smaller and half the elements are bigger, then do their values actually matter? No, right? Because you only care how many are smaller and how many are bigger. So this is your next observation, that values do not matter in median based problem. If you have done like some sort of initial transformation before, right? Values do not matter. And why does value do not matter? If you have, this is a big if you fix median, like if you do not fix median, then of course the values would matter, but if you fix the median, then the values would not matter. So if the for a fixed median, you only care about how many elements are smaller, how many elements are bigger. So you must have seen this kind of pattern in my previous videos as well. I think in one of the Brain Gym series, I had uploaded a video where we wanted to find out in a particular uh, substring how many substrings are there with an equal numbers of 1 and 0. So we did some transformation and we said that we will convert it to a known territory, which was replace zeros with -1, and you will get a string with 1 and -1, and then you are asking the question how many subarrays exist with the sum 0, and then we again transformed it to a difference array world because that was easy to solve. So here also you can get this similar hint that since their values do not matter, you can have this transformation. Like this is the central element x. You define it as your baseline and you mark x as 0, and all the elements that are above the baseline you call them as +1, and all the elements that are below the baseline you call them as -1. So now you see that we have already done the transformation, and the transformation is now you have to deal with an array containing 0, 1 and -1, and this is the world that we are most familiar with. We already have a lot of studies around these kind of structures and a lot of algorithms to help you that deal with an array and numbers. So it will have -1, 1, 0, it can have 1, -1, 1, -1, and so on. Now, what can you say about this array? So if our interpretation, that is median resides on the center, this is the baseline, and all the elements with all the elements that are greater than the median reside on the right half, upper half, and all the elements smaller than the median reside on the lower half. But for it to be the median, we already said that every element should exist as a low comma high pair. That is, the upper half size should be equal to the lower half size. So now you can already see we are making some progress. Like if you define all the upper half as +1 and all the lower half as -1, then the sum of this 0, if the sum is 0, it means that the median is x, but if the sum is not 0, then the median is not x. So there are some nuances to it, though we will come to it later in the video, but for now you can clearly see that this observation is correct because every element will exist as a low comma high pair. Now remember, we were trying to try all x, and then we said that okay, we will only try x equal to the median of the original array. We will fix it, and then we'll try to find out how many subarrays can we split into such that their median is also x and the number of blocks is maximum. So what is the transformed problem that we are solving over here? Given an array consisting of zeros and consisting of 0, 1, -1, find the maximum number of blocks such that, what are the conditions? Let's see. First is that the block should have equal number of +1s and -1 so that they cancel out and their median becomes the baseline, which is 0. So we are trying to find the answer to this. Block has sum 0 so that all the higher element and the lower elements cancel out. But there is a catch to it. If you are smart enough to notice that the catch is you could have like +1 +1, like you could have something like +1 +1 and -1 -1. They cancel out, but their median is not 0. Why? Because the median, the central element itself, is missing. So block has sum 0 is not the only constraint. You should have another constraint, which is this subarray should have at least 1 0, or I should say the block should have at least 1 0, right? And the third constraint, of course, is that there should be no ambiguity, which is to say that the block length should be odd. Block length should be odd. So how do you solve this? So first of all, you might try to apply some greedy strategies. For example, if you look for the first block, this is your array. So where can the first block end? So of course the first block will end when the sum becomes 0. It cannot end before that. So suppose this sum becomes 0 over here. This is sum equal to 0. So if sum is equal to 0, it makes sense to cut a block over here, right? Because this will have median as x and it is not influencing any elements on the right hand side. Why? Because of that merging logic that we discussed. Because no matter how much you extend it, half the elements are less than x, half the elements are bigger than x. So the resulting median on the right hand side will not be affected if you insert a low high pair, right? This is just like inserting a low comma high pair. But again, just like we have discussed in the previous slide, that there is one condition that we are missing, that the block has to have at least 1 0. So just because you have seen the sum as 0 doesn't mean that you can end the block over here. So okay, now you modify your conditions and say that okay, if the sum is 0, you will end your block. And the second condition is that the length should be odd, then you will end your block. Length is odd. And you also add a third condition saying that the 0 seen or not, right? If 0 is in the block, you end your block. Otherwise you keep on continuing the block until you see a 0 and until you see a sum equal to 0, and then you see a block of odd length. So this is the first greedy approach that comes to mind. But is this correct? I mean, this looks correct from all aspects, but remember that the problem said that the entire array should be split into blocks. No element should be left out. But the problem with this approach is, so if you greedily end your block, so what happens if you encounter this situation? You receive 1, -1, and you receive 0. So you can see that in this block, all the conditions are satisfied. You have seen a 0, the block length is odd, and the sum is also 0. So you create a one block greedily over here. But the problem is, if you do this greedy construction over here, the other elements might suffer because they were relying on this particular 0 to help them create the median that they needed. Like what if you had this situation out there, like 0, -1 and 1. So now these two are helpless. They cannot do anything, right? So they also actually needed this, right? They also needed this to construct it. So that's why if you be greedy and then you take all the zeros for yourself, or you take the first 0 for yourself, these elements also needed that 0, because what if they don't have a spare 0 in their own block, say? So greedily cutting a block over here is not correct. It might be the case that in the worst case, see, in the worst case anyway, the entire block is an answer, because the entire block has median m that we are looking for. So the minimum answer is of course 1, because an answer definitely exists, that we know. So that's why if you greedily cut a block, that is not correct. So this is one greedy idea that of course does not work. And to fix this, you might also try thinking of other approaches, but they might also not work. So I'll directly jump onto the solution that works. So here we see that we were being greedy and cutting the block as soon as we hit all of these conditions. But again, the problem is the elements that come after it, they get influenced. So whenever some kind of, like, whenever this situation arrives, like, you have some trade-off to make. Like you can either cut a block right now and then have one extra block for yourself, but then you negatively affect the future elements. But other choice is that you don't cut a block and then you keep on extending, but then in that case you are negatively affecting your chances to create as many blocks as you need. For example, what if you did not cut a block saying that okay, this condition that can happen, so you say that okay, some future elements might need this zero, so let me continue. But what if the future elements don't need your zeros at all? Like why, what if they have their own set of zero? So in that case it would have made sense to cut a block over here. So right now it's not clear whether you should cut a block when all these three conditions are satisfied. So this means that at each block that satisfies all of these three conditions, you have two options. You can either cut it or you don't cut it. So that is why the dynamic programming comes into picture, because in dynamic programming you don't have to make a greedy choice of cutting or not cutting and then regretting later. You can actually do both at the same time. So you cut a block and then you see what happens, and then you don't cut a block and then you see what happens, and then you take the best outcome from these two possibilities. So how do we solve this with DP? So remember, with DP you don't have to make any greedy choice. You have to basically explore all the possibilities. And in my earlier brain gym videos also I have discussed this concept a lot of time, that whenever you are dealing with these kind of DP problems, just assume that you have split these array into several smaller blocks, let's say, and you want to know just you want to know the answer to the one simple question, which is if you append an element x over here, right? If you append an element, like let's say this is the ith element that you are appending, and this is the ith element you are appending, and you have already computed the answer for everything on the left hand side, but we will see what computing the answer really means. But suppose you append one element to the array, and I ask you that okay, I have all the answers that you need, whatever the question may be. Right now I'm saying that you have already computed the answer, but we don't know the question, like what is exactly the question. But I'm saying that for dynamic programming problems, you don't have to assume a question. You just say that you want to append an element and you want to uh, ask some questions from the left hand side, and the left hand side will be able to give you the answers for all of them. So what is the question that we want to ask? The question that we want to ask is, for this entire array, how many maximum blocks can you split into such that the median of each block is equal to x? This is the question that we want to answer. Now, since we appended this element, and this is a very common DP pattern where you append one element and then ask this question, in that case it makes sense to worry about the last block instead of the first block, because here, say, when you do some greedy strategies always start from left to right most of the times. But for the dynamic programming, even though you can technically do dynamic programming by uh, appending or prepending an element at the start, but usually the convention is that you append an element at the end and you worry about what is the optimized answer when you introduce a new element. So when you introduce a new element, you make some choice about the last block. So we don't know where to end the last block, right? Just like we did not know where to end the first block. So let's see, but there are only very limited places where the last block can end. And what are the places? The last block can end over here, or let me do something like, so suppose this is the last element that you have inserted. So the last block, this could be the last block, this could also be the last block, this could also be the last block, this could also be the last block, and so on. But there are only O of n possibilities for the last block, right? And out of this, not all of them will be valid. For example, this block, this cannot actually be the last block, even though we are saying, because its length is odd. So remember, it has to satisfy these three constraints. Length should be odd, sum should be 0, and you should have seen at least one 0, right? So that you see this baseline over here. for it to actually appear as a median. So, okay, then assume that there are some blocks that satisfy all these three conditions, and those blocks are, let's say, these are the blocks. This is one blocks that satisfy both the condition, and this is the other block that satisfies both of the condition, and this is the, like, let's say, the last block that satisfies all the conditions. Now which block should you make the cut at? Like we said, we don't know, right? We don't want to make some greedy choices and then regret later. But what if you do decide to make a cut at this? If you do decide to make a cut at this means that this entire section has length, has odd length, has median x, and has sum 0, right? That's why we made a cut. But once you have made a cut for this, what is the question that you are interested in asking? You are interested in asking what is the maximum number of blocks that you can cut from this prefix, which is exactly the question that was asked to you in this round. Like, the question that was asked to you, what is the maximum blocks that you can cut in this bigger prefix, and now you are asking that same question back to that same person, and you are saying that, okay, if you tell me the maximum block that you can cut your smaller prefix into, I can tell you the answer to my question, the question that was asked to me. Similarly, if you decide to cut a block over here, if you decide to cut a block over here, then you are interested in what is the maximum parts, what is the maximum blocks that you can split this smaller prefix, and then you repeat this for this cut, this cut, and this cut, all of these three cuts. And which cut should you prefer? Whichever cut gives you the maximum benefit. And why is this not a greedy and optimal, and why is it an optimal approach? Because these were the possible cuts, but you did not make a choice. You said that, okay, if I were to cut this over here, would I have regretted this decision? So you would not have regretted, because the answer would be present in this prefix, this dp prefix, and the answer is present over here, and the answer is present over here. So you pick whatever is the best answer available to you, and then you update your answer, because the question that was asked to you was what is the maximum cut in this larger prefix. And now you can see that why do we say that in dp the question is not fixed? Like, when you append an element, the question is not fixed. The question that you want to ask to the smaller prefixes, as long as you can answer the same question for the bigger prefix, then you are good. Like, you can assume that the answer to that same question on the smaller prefix does exist via induction. So this gives us a very clean O of n square algorithm, because there can be a total of O of n possibilities for the last block, and once you have computed that, you are only interested in finding what is the optimal answer to cut this smaller prefix. Now it is possible that this smaller prefix cannot even be cut. For example, if this prefix has become of length 2 or length even, or there is no cut where every block achieves sum 0, or every block achieves a 0 element scene, etc. In that case, you want to say that, okay, there is no possibility, so what is the maximum number of block? Like, you could set it as minus infinity, so that nobody can be encouraged to actually perform a cut over here. So this is actually a very common dp technique. Whenever you want to whenever you encounter an impossible transition, but you don't want to do some case analysis, you set the dp value as minus infinity, so that nobody can actually dare to make a cut over here, because they will face a lot of loss. So they might instead try making a cut at someplace else. So with this in mind, let's implement the approach. So you take this array, and we already discussed that the x that we are dealing with would be the median of the original array. So we make a copy, sort the element, and find the middle element, which will act as the median. And then we said that for solving median related problems, you always have to transform it into a known territory which is if the element is equal to median, that is the baseline, you set it as 0. Higher elements get a +1 and lower elements get a -1. And then you define dpi, and like I said that dpi is the answer for this prefix. And what is the question? The question is, what is the maximum number of blocks that you can cut so that each block has median x? So that's why we say dpi is the maximum part that the ith prefix can be split into such that each part has equal median. This is the dpi definition that we have defined. And we know that for each time you want to add an element, you keep extending your last block by 1, and you track whether you have seen all these three conditions, whether you have seen a 0, and whether the sum is actually equal to 0, and whether the length is equal to odd. So this is the odd length condition, this is the existence of at least one copy of the median, and this is the sum is equal to 0 criteria. And if any cut achieves these three correct criteria, then the question is that you are interested in asking that, okay, if I go ahead and make the cut right now, then the left hand prefix, what is the maximum benefit that I can get from the smaller prefix? So that benefit is nothing but dp start -1. Start is this index, like this is, call this as s, call this as I. So you are saying that the last block is s comma I, and s can be anything that is to the left of or equal to I, because block could be of single length as well. So that's why you start iterating s from I down to 0, and you track whether you have seen 0, and you track the entire sum. And then dp of I is nothing but you have created one block over here. So the answer to the original question, which is dp of I, means maximum number of blocks for this entire larger prefix is nothing but one block that you already created and the other blocks that can come from here. Now some of these blocks creation might not even be possible, in which case you initialize it with -infinity so that you will not be encouraged to take the transitions from those dp. And finally you print the last element of the dp. Why the last element? Because the original question was for the bigger array. They don't care about the smaller prefix. For the biggest array, what is the maximum number of blocks that you can create? And that is by definition dp of n, or dp of n-1, depending upon which 0 based or 1 based indexing you are targeting. So yes, this was it. Like this is how you solve like median related problem. Like you convert it to +1s, 0s and -1, and then you apply some known algorithm and data structures like two pointer that we just applied and dynamic programming. But all this is good, all this is correct. There is one nuance that I already talked about earlier when I said that this sum has to be 0, and like we'll talk more about this in detail. And this is actually one catch with median related problems that we usually miss. And in fact, if you have seen my brain gym videos, I have created two videos on brain gym series where we saw that missing some, like missing some observation regarding duplicates can lead to a lot of problems. And both the algorithms that we have discussed, like I think the problem name was greedy algorithms. So in the greedy algorithms, you had seen that sometimes we tend to forget the duplicates, and that actually might form the base of your algorithm. So here we are saying that we need to satisfy three conditions: length 0, whether you have seen a 0, or whether the sum is 0 or not. But I'll show you why this code is kind of correct, but there is some cases that it might fail, because this interpretation that we have just defined, we said that in this interpretation we said that this is the baseline x, and this is the higher elements, this is the lower elements. All these lower elements get -1, all these elements get +1, and we said that the sum is equal to 0, means median is equal to x. Not just this, we also said that x should be seen, right? X should be seen. So this condition is still correct, right? This condition is still correct. This is sufficient, you can say, but this is actually not necessary. This is actually not necessary. So even though in this entire video I have been talking about sum as being 0, and some of you might have already noticed that, but actually sum being 0 does not, I mean sum being 0 is sufficient and ensures that the median is x as long as you have seen x. But there are other cases that median could be x where sum is not equal to 0. For example, if you had something like this, you had -1, you have something like this, you had -1 and a 1 to cancel it out, and then you had an extra 1. So you can see that the sum is what, 1. So you can say that, okay, this, the median of this set cannot be equal to 0, right? Because you have not seen a 0. So let's insert a 0 over here. Now, of course, even now the median is not 0 because set length is odd. Set length is even. So I insert another 0. Now you see the sum is actually 1, right? Because 1 and -1 cancel out and this 1 remains. So the sum is actually 1. But what is the median of this set? So if you sort all the elements, and all the elements I think are already sorted, what is the middle element? Middle element is actually 0. So you see that there are like as many elements that are smaller than it as there are elements that are greater than this. So the median of this set is actually 1. So the sum of this element is 1, but the median is actually this baseline 0. This means that we have missed some cases wherein the sum cannot be 0, could not be 0, but still the median can be x. And why did we miss all these scenarios? Because we, every time we operated under the assumption that there is only one copy of the median in the array, right? And that is not true, definitely, because when we added this condition, we said that every time you see a copy of a median, you set it to 0. So in these kind of median related problems, it's very easy to forget that median can also have multiple copies. And in fact, we will refine this statement. Now this doesn't mean that all the DP idea etc that we have done or discussed is incorrect. I will show you that this entire code is still 99% correct, just needs fixing a bit, and I'll show you where to fix. I did not introduce this concept earlier because I just did not want to complicate things. But okay, let's talk about it. So if the sum is 0, we know that that is sufficient, that's good. But if the sum is not 0, so suppose if the sum is s, this means that all the plus ones and -1 cancelled out, otherwise they would have appeared in s. But there are a total of s elements that could not be cancelled out. Like these elements had a corresponding pair over here, they got cancelled out, and these elements, their count is s, they did not have a corresponding pair to cancel out. So when we say that we push numbers down on from the baseline and then we push numbers up from the baseline, depending upon whether they are bigger or smaller than the median. But what about the numbers that are equal to median? So if something that is equal to median, you have freedom, you have complete freedom to either push them above the baseline or you can push them below the baseline. This is the baseline for x. So if x numbers on top are unpaired right now, and if you have at least s copies, if you have at least s copies of the median, extra copies of the median, like you of course need x here, but if you have extra copies of the median, then you can push all of these numbers down to cancel out this x. So if you have x copies, s copies at least, you can push them down. But what if you have more than s copies? If you have more than x copies, no worries, you can place all the x over here on the baseline and they actually do not change the median. But if you had less than x s copies of the median, then you actually cannot cancel out these many elements by pushing elements downwards, and the median of this set will not be equal to x. So this is when you have more elements on the top side. But what about the case where you have more elements on the bottom side? Like suppose these elements got paired here, but there are these many elements that are remaining, so the sum will be -s, right? So if the sum is -s, then it means that there are total of mod s element, like absolute value elements, that are unpaired on the right hand side. So if you have this many copies of the median, you can just push this copy here and pair it with this, and it will cancel out. But if you do not have this many copy, it will not cancel out. So the actual algorithm is that the sum is equal to 0. That is sufficient but not necessary. So that's why we shouldn't enforce this condition. Actual condition is that if the sum is equal to s, then if the median copies, or median copies is what? The number of zeros that you have seen. So far we have only been tracking if we have seen at least one zero or not for the baseline to be created. But this time we actually have to track how many zeros have we seen. So if you can see that if zero count is greater than or equal to the absolute value of s, then everything would be paired, right? And since the interval is odd, then of course we are also tracking this whether we have seen a zero or not. So since the interval is odd, or of odd length, then we will have one median remaining to cover the baseline. So this means that the actual condition is not sum is equal to 0. The only change that you have to do is this: 0 count greater than or equal to the sum. This denotes that the median of that subarray is equal to 0, and 0 meaning the baseline that you had created. So this is just something to keep in mind for future median related problems, that don't just go on and say that sum is equal to 0 means median is equal to 0. Yes, it does mean that, but not the other way around. Like median is equal to 0 doesn't mean that sum is equal to 0. And what does it actually mean? That the zeros should be able to push things from the down to the baseline, or further up the baseline if needed. So we'll take this same idea and fix it. How do we fix it? Instead of tracking whether we have seen a zero or not, we'll track how many zeros we have seen. And instead of adding just this condition that sum is equal to 0, we'll say that the unpaired elements, which is the sum, absolute value of sum, right? This should be smaller than or equal to the copies of median that we have seen. So this is the final algorithm, same as before, but this time we are tracking the zero count, how many elements we have seen for the last block. Suppose you cut the last block over here and you want to ask, okay, from this left part, how many blocks can you cut? So you see that the length should be odd. That is the first condition. The length is odd. Second condition that is that you have to see at least one copy of the median. And the third condition is that all the elements that are unpaired, like all the elements that do not occur in a low high pair, they should be able to cancel out by the median. And what is the median? Median is the zero count. So you count the frequency of the median and they should be able to be cancelled out from this baseline. So if there are s extra elements that are remaining, you should have at least as many copies of that as x, so that you can cancel it out. And same for this, like if you have minus s sum, so minus s sum means you have s extra elements remaining, so you should have at least x copies. So that is why this absolute thing is coming into picture. This is nothing but just mod. So you see that our idea was indeed correct, just had to change to 2 to 3 lines to fix this. Doesn't mean that original thinking was wrong, but it did simplify the discussion, like every time when we kept talking about that sum is equal to 0 thing. But in future you should keep in mind that duplicates means sum should be less than or equal to the copies of median. So this was it for the video, and you can see that this medians, they don't have a playbook, but once you come to a familiar world of 1 zeros and minus 1, we have a lot of playbooks to solve these kind of problems. And maybe in future this transformation might help you. In fact, a lot of problems with medians involves binary search. And in binary search, here in this problem, even though we said that x does not need to be tried for all the elements of the array, because x will be equal to this median, in some of this problem x might not be obviously the median of the original array, but you have to remember that the fact that the median of any block or median of any set resides inside the set. So you can actually do some binary search for the median and solve some problem. So there are some practice problems. If you need them, do let me know in the comment section. I will link them down. And yeah, if you want to submit this problem, you can also do it on Codeforces. The link will be present in the description.